Welcome back, Precalcsters. There we go. Today we're going to continue on, and we're going to look at 3.5, and it's using exponentials and logarithmic functions to create models for real-world situations. Before we jump in with that, are there any types of problems from yesterday that we didn't have time yet on the homework to go over that you would like to look at? Do we want to do any additional log stuff just to help us out? Or by virtue of doing more problems, is that going to be sufficient? Okay, so we'll do more problems. We'll have a review day and stuff. I don't know that we're going to finish the chapter today, but we'll see. In 3.5, eventually, in 3.5, let's do that. Our focus is going to be log and exponential models. All right, what class is this? Precalc. There are ideas that we have access to that are applicable in a lot of different places that we are not going to look at entirely. My goal for this class is, I guess I have two main goals. Two, to make sure we refine and clear up any mathematical understandings that you have prior to taking calculus. And then the second goal is to prep you for calculus, because this class is not required. I assume that most people who take this class, not always everybody, but most people are probably going to wind up taking calculus, and that's what I'm prepping you for. Just so you know, like, my motivation for stuff. Calculus, I've said it before and I'll say it again, I think it's easier than this class. This class does this, and all over the place. It's challenging. Calculus does not, which is much nicer. So, as we go through, we're going to take a look. Our first main section with these log and exponential models is, it turns out there's a lot of different models that we can do, or that we can deal with right now. We're going to say 5 models, and these are just equations, but then in parentheses, I'm going to say 2 that we use. Specifically in this course, prepping for calculus, there's only 2 models that we're going to look at real hard, but I want to make sure that you can see all 5 of them. All right. For these 5 models, there's really only 4, but we'll shove 2 of them together. One of the ones that we deal with, and I'm just going to write them all out here. The first one that we deal with, and I think it's going to be a tilde. We're going to say exponential. Now, your book splits this up into 2 different ones, and these are the 2 that we really use. We primarily use exponential models. Now, these guys are going to take the form y equals a e to the bx. Okay, in this situation, if we have y equals a e to the bx, I'm going to just do 2 little branches. The first one's up here, and we're going to say if b is greater than 0. If we look at that model, and I have, don't even care, let's deal with a 2 for the first one. If I say 2e to the bx, where b is a positive number, do you think I'm getting bigger or smaller? Like if I do 2 times e to the 1 and 2 times e to the 2 and 2 times e to the 3, it's getting bigger, right? Okay, if we have an exponential that's getting bigger and bigger and bigger, do you guys recall what we referred to that as? Starts with a g and ends with roth. It's growth. Cool. We have exponential growth. In the situation that possibly b is, and I don't want to say less than 0, but we will. I'm okay with that. B is less than 0. What do you think we're going to call that? Decay. This is the primary model that we're going to deal with. Beyond this, just so you know, there are 3 more, and I'm not even going to write them down, but I want you guys to be aware of them, okay? There are 3 more models that show up and are really handy in modeling real-world stuff. Exponential growth and exponential decay, these first 2, these are common, really, really common. This example here is what I shoot for with your grades, just so you know. This is a standard distribution. It's called a bell curve. Really common. If you were to take any population, you're going to see about 70% of people are pretty close to that middle area. That's where most of the area is. Smaller areas as you get to the ends. This is used in statistics pretty commonly. This one right here is known as a Gaussian model. Carl Friedrich Gauss. We'll talk about Gauss this year. He did some awesome stuff as like a 10-year-old. Cool. We also get this lovely logistic growth, where this is more akin to like real populations. Human populations getting big and big and big and bigger, bigger, right? It's happening. Can it get big forever? Why not? Oh my, resources will run out and all of a sudden the population can't grow anymore. This is what real population models look like. They don't expand forever. They reach this carrying capacity and they stop. This is known as logistic growth. The natural log model, well, we'll use from time to time. These are just logarithmic models. These other four exist: Gaussian, log, natural log, but these are the ones we focus on. Cool with that? All right, which means everything that we do will have some relation to our exponential stuff. So we have a ton of examples, and it's all that we have to do today, or get to do, however you want to word it, applied, or applications, if you will. If we think back to how we wrote stuff, I'm going to do a quick recall little piece in here. If we're talking money, specifically with compounding interest, we're going to write our formula like this. A of t is equal to, gosh, compounding interest, one more time, what sort of deal is it? Pretty good deal. And it's continuously compounding, so we wouldn't even have to worry about the yearly. PE to the RT. Okay, this is money. If we're looking at populations, there's a few different ways it can show up. Typically, you're going to be able to model a population at time t. So I would just use P of t equals AE to the KT. Whether my population is growing or not, those have very different letters, but do they look the same equation? A and P are interchangeable here. R and K are interchangeable. A of t and P of t are interchangeable. Cool. The other scenario or situation that we deal with pretty common is radiation. There we go. Radiation. Now, depending on the values that we're looking at, I like to name my functions so they make sense within the context. A of t I use for the account balance at time t. P of t gets used for the population. And then radiation, I would probably use A again, but I'm going to. The amount at time t is equal to A naught, typically gets used here, E to the KT. They're all the same. Just a reminder that A sub 0 is A naught, and it's not like NOT. A sub 0, if you want this, you can have it. It's A naught, N-A-U-G-H-T. That's the word that we're using. You could use initial. We could tweak this one if you want and say, hey, the final amount is equal to the initial amount times E to the KT. If you wanted to, we can adjust this. Whichever one you use, doesn't matter to me. They're all the same. Okay. I don't care which sort of problem we do. Do you want radiation, money, or population? JV, what do you want? Population. Here we go. All right. We are going to be dealing with a bacteria population. So here we go. Example A. And I'm going to pause it for a little bit editing stuff. So this can be challenging. I'm going to jump in right now and let's just decide on the model that we're going to use. Everybody cool with using the population model, the population at time t? In this problem, t is measured in what? Hours. So we'll just write our general model. And this, it feels like a physics problem. I could say equation if you wanted. I know that the population at time t is going to be equal to AE to the KT. Cool. It's been a little while, but let's just go ahead and check this out. We know a few different things. Specifically, do we know the population 2 hours after inoculation happened? So I'm going to write that P of 2 equals what? 256. This means at time t equals 2, or 2 hours after my experiment started, I have a population of 256 bacteria. Do I know any other values of my function p? Good catch. P of 7, I also know. Why is it P of 7 and not P of 5? Yeah, it's 5 hours after we checked at 2 hours. So P of 7, I think, is 541. Cool. We don't know K. That's a bummer. We don't even know A. We don't know how many bacteria we introduced initially, which is kind of a bummer. But we'll figure it out. Anything else that I know? I don't think so. What am I trying to find in the end? So P of 24. Now, there's going to be some work that we need there, because not only do I need the population after 24, what do I need out of this equation? I know what E is. It's E. I know what T is. It's 24. What other values would I possibly need to be able to answer this question? But we need A, which is my initial population, my starting amount, and we need K out of this, right? All right. Here's the bummer. We have two unknowns in that equation. How many equations do we have? That's a good answer. That's what I was expecting everybody to shout out. Right now we only have one. So it seems like maybe it's not doable, but we're going to use some algebra that I don't think we've had to look directly at this algebra this year, but let's just get started. Let's try it. Okay, I'm going to plug in what I know, and I don't care whether we start with P of 2 or P of 7. Which point would you like to start with? 2 feels like the natural choice. So if we're looking at this, I'm going to annotate like crazy. Let's use P of 2. That says us, but I'll change it. Let's use P of 2 equals 256 to write, and we'll just stop here, and we're going to write it out. I know that the population after 2 hours is 256. And that is equal, according to my equation, the population at 2 hours is A, don't know what that is, times E to the K times, how much time has passed? 2. It's annoying to write K2 for me. I typically write 2K, but it's the same, right? Before we move forward, any questions with how I've obtained this? All right, we'll see here in a minute, because I'm going to make you write another one in just a moment. I have two unknowns, unfortunately. I'm going to leave a bit of space, and I'm actually going to work off to the right just because I have space to do so, and I'll just move everything so I can keep it here. I want you guys to do something similar, but with P of 7 for me. So at your desks, I want you to now do the same thing. Use P of 7 equals 541 to write. And I'm going to give you guys just a moment. I'll come around and look over your shoulders just to check it. Talk it out if you have no idea what I'm asking. Who could probably help? I think I could help. Cool. I'll give you a moment. If we do this, I think I get 541, and we just spoke about this, but 541 is equal to AE to the K times 7. All of a sudden, how many equations do we have? 2 equations. How many unknowns? Well, by George, I think we can probably work this out then. It's just a matter of how do we do it. Okay. Typically, when I do these problems, just so you know, I only do the blue part first. And then I work with that, and then I work with the green part second. But I just want to make sure that we have it. If you have 2 equations and 2 unknowns, you can set up a system of equations. Okay, lots of fancy language going on here. It's going to be so much easier than it sounds. I typically always default to solving for A first. I want to know my initial amount. That's my first goal. I want you guys to solve this equation, the blue one, for A. You're not going to get a number. You're going to get an expression. Solve for A. I'm going to give you a head start. I want you to do that. Show me you can undo an exponential. Or solve. That one's super easy, I suppose. You're probably all done. Huggins, you might have zoned out there for a second. I'm going to show you because it's super easy and you're going to be able, like, everybody's going to be able to do this. E to the 2K is just a number, right? and it's multiplying by a. If I want to solve for a, what would you divide both sides by?
E, K, 2.
Good. That's all I'm going to do. Yeah. Now I'm going to make this look a little bit nicer. There's not even any work I can show. I'll stick with blue. Do you guys agree that this becomes a is equal to 256 divided by e to the, and I'm going to rewrite it as 2k now. Everybody on board with that? Now, this feels unnatural, but maybe this part doesn't. How do you solve systems of equations? What are the two techniques that you guys have? It's been a while. I'm going to tell you, and you just let me know, like, yep, I remember. Substitution and elimination. Do those sound familiar? Add them up, and something falls out, or you substitute it in so that you only have one variable. Can we rewrite this green equation using this a value? Now, what I mean by that, and we'll write it here, and this is going to look weird for a second, plug this in. Which means in this equation, we obtain instead 541 equals, what do we just decide a was? 256 divided by e to the 2k. So that's a, that's it, times e to the, how many k? 7k. As soon as we do this, notice what happens. I have a single equation right here. How many things in this equation are unknown? Just one. It's just k, right? Now, we did not hit the exponential stuff super duper hard because it was pretty clear that you guys remembered most of your properties. I want you to tell me, and I'm going to write something. Before you write this, decide if you need to. Like, check it out. I would rewrite this like this. And when I think about this in my head, I do rewrite it like this. Can anybody tell me why I would rewrite this in this fashion?
Just to collect like terms.
So maybe to collect like terms, but more specific, something's going to happen with them. What's the exponent rule here? If it's e to the something divided by e to something.
The one-to-one property. No.
So you're close. You know the log property already, and you're probably stuck on that more recently. If we have division in our argument, that comes from what between the logarithms? Subtraction. So if we see the exponential form, they're dividing. The exponents must do what? They subtract. I honestly don't really write this every time, but check this out. If we just subtract, I wind up getting 256 e to the 7k minus 2k? 5k. Not looking too bad at this point. Or it's looking awful, and it's going to look a little worse here in a second. What do you think I'm going to ask you guys to solve for? So I already know e. It's 2.71828, blah, blah, blah. E is just a number. It's an irrational number just like pi. K. Unfortunately, right now, k is stuck where? Man, if only I had a way to undo an exponent. I'm going to take the log. You have a decision to make, though. If we're trying to solve for k, or any variable for that matter, primarily the way that you've always gone about it is making sure only k is on that side before you start to try to solve it. How do I get rid of it, something on the right side of this equation, so that only stuff with k is on the left? Whoa. Only stuff with k remains.
Does it have to be on the left?
So I don't really care what side it's on, in all honesty, because I can work with it. But if I divide both sides by 256, and I'm not going to touch my calculator yet, that's what this side is, yeah? Equals, what's on the right side? All right. I would always isolate this variable when possible. Now it's just a simple problem of how do we undo this? So I don't know k yet, though, right? I'm trying to solve for it, and it's stuck in the exponent. How do you undo an exponential? Not a square root. That's how you undo a square, or a cube root would undo a cube. This thing changes. So So you used, Kalisha, just so you know, when you gave me that square root symbol, you identified with, not as wordy, the inverse of a square is a square root. That's what you're using that fact. What's the inverse of an exponential? A log. Can I take the log of one side of this? As long as I do what? Take the log of the other side. Now, it doesn't really matter what log you use. You could use log base 4 if you wanted. I wouldn't. Any idea what log I'm going to use?
Natural.
I'm going to take the natural log of both sides of this. So here we go. It becomes a natural log of, and I'm going to try my hardest to just rewrite this, 541 over 256.
I keep thinking this question's gonna end.
We're getting there. It'll go so much faster once we do one, I promise. What happens on the right side of this equation, JV? If I take the natural log, any properties that you can see already just waiting to happen? Oh my gosh. You're absolutely right. I'm going to write it a little bit more though, because you are correct. If you want to just think about the ln and the e falling out, love it. I think about it like this, and now it's gone. Just a reminder, if you were looking down, I moved the power out front because that's my power property. And then what's the natural log of e? 1.
Or
1.
Yeah.
E to the 1 is e. Gosh, so this is just gone. If you want to solve for k now, one last step. You are going to divide. On your calculators, go ahead and get me that value. It's ugly. I'm just going to put it right here. K is equal to, and we're going to go to 4 decimals. Natural log of 541 over 256 divided by 5. Make sure you close your right set of parentheses.
0.149. That might be wrong.
Let's go 4. I believe your number.
0.1496.
0.1496. Somebody second that? Okay. 0.1496. Okay. First off, this value of k, positive or negative? Which indicates it should be growth, right? Is our population growing as time goes? 250, 60? It is growing. Okay, I'm convinced. All right. Huggins, you made a comment a minute ago. I keep thinking this problem is going to be done, and it's so close to being done. I want you to put a star next to this. And I'm going to come over here, and I'm going to put a check mark next to it. We got k. This next part goes so fast. Yeah, check it out. I'm going to go back, and I didn't tell us to put a star in it yet, but I have an expression right here that says if you know what k is, you know what a is. So here we go. Using your calculators one more time, you're going to ask it, all right, calculator, what is 256 divided by e to the 2 times 0.1496? And I have different numbers on mine, so somebody's going to have to hook that up. Which one? This one? So this is from that first part that we did where I solved it for a. I then substituted that a in here. I've solved it for k, and now I'm going to use that k value to go back to this blue one and solve it for a again. So it's kind of like a back and forth, but that's what always happens with substitution. Plug in x, solve for y, plug it in to get the x. This is just a bigger substitution problem. I have no idea what this number is, but somebody can shout out their answer.
189.80.
So 189.80, and then let's think this out. 189.80 initial bacteria. Can you really count 0.89 of a bacteria? So it feels unnatural, but I'm going to round this down to be 189, right? 189 bacteria. This is my initial population. We started with this many. Okay. We are so close to being done. We have everything that we need. Every single part of it. I'm struggling because I have this space here. But notice what we've just done. We found A, we found K. Do we now have a working model then? So here's our working model. Working model. And let's see. Apparently the population at time t for this bacteria is 189. That's my initial population, my A value, times E So the what was K?
0.1496.
And I'm going to multiply by T. Here is my true model. I can now predict and reason out the population at any time T for this bacteria, assuming that it's allowed to grow forever infinitely large if we wanted it to. If I now want to know the population after 24 hours, you're just finding me P of 24. So I want you to use your calculators. After 24 hours, there are, and I don't know this number off the top of my head, we'll just say approximately, and you're going to give me a number, and I want to verify we can all get the same number. Yep. I'll just tell you right now. If you're dealing with a population, round down. If you're dealing with money, round down, because that's what the bank is going to do. Cool. Round down every time if we're doing these problems. And to be honest, Sean, if you guys, I would get a different answer if I typed it in, if I did this whole problem on myself, because I would never actually round K. I would use natural log of 541 over 256 divided by 5, and I would plug that back in, and I'll let my calculator round it to 50 spaces or whatever it can do. Like, if you're close, I'm not going to destroy your rounding. I have no idea how big this population gets after 24 hours. I still have no idea, because that just happened. 6,940 or 69,000? 6,940 bacteria. Can somebody second that?
That's what I got.
Interesting. So notice, 6,000, don't erase anything. 6,000 what? Okay. Why do you, like, these are pretty close. Why do you think they're different? What did you round K to? Yep, that little bit of rounding, just 4/10,000ths, changes this number wildly. And Sean, this highlights just what I was getting at. I'm going to, I would accept either of these. Cool. Should we try another one like this, or do you want to see the same exact type of problem applied differently? Well, we already did all this, right? Do you still have space on your page? Bummer. All right, we better do a different one. Just so you guys are aware, I'm not going to give you any homework tonight. We're just going to work for 5 more minutes. Tomorrow, I will give you an assignment to practice with this stuff. And then we are going to knock out a team test on Thursday. Remember, if you want to get started, I'm going to hook you guys up, and you can get started today if you want. Both sides of this. Both sides of a big one for this chapter. Cool. All right. One more problem. Before we do any parts of this, it's ugly because the way it was forced to work in here. Does this seem super hard, doable? What do you think? Okay.
It's just a lot of steps.
It is. All right, example B. And we're going to be super like caveman language here. Element alpha has half-life of, let's make it like, I don't know, 30 years. All right, so we have an element that has a half-life of 30 years. Pretty cool. I want to know if we started, or if we had, how many grams initially? Sure, 13 grams initially. How much left after, do you want to do a century or millennium? Okay, after a century. very different context, right? But it's not mathematically. Mathematically, it's the exact same idea happening here. If we have this, we have a ton of stuff that we can deal with. Now, first off, I need to work out the model that we want. And I don't care how we write it. Does anybody have a preference to which equation we use? I probably wouldn't use P of T because that's population. Do you want AF equals AI? Or just Y equals A naught? Or if you don't like having to keep them separate, weird. Can we just use this? If you just prefer to work with just the model that doesn't have letters and stuff, would this work, you think? Cool. What does A represent in these equations? Initial amount. So check it out. What is A in our problem? 13 grams. And it kind of seems like we can't go any further. That's literally all I know. It's kind of all I know. I need to find K, right? I already have A. All I'm after is K then. And we're going to do this problem a lot less formally structured like we did the other one because it's the same idea. The structure is there. We're just going to apply it. Man. Well, hypothetically, if I let it go for 30 years, do you guys know how much would be left? So can you be specific? After, and you can write this if you want to, but after 30 years, we have 6.5 grams. Do you guys agree with that statement? That's the half-life. That's what it means. So check this out. Let's just let this run through one half-life and see what happens. Specifically, we're going to take this equation and we're going to use 30 years. So if you would like it, and I prefer this, I would call this y of 30 equals 6.5. Just so I can see that, hey, look at this. These are really ordered pairs that we're dealing with. 30, 6.5. All right, well, let's just plug in. I know that after 30 years, I get 6.5 grams left. Do you know how much we started with? We started with 13 grams times e to the, I still don't know, k. How many years did we go?
30.
You think you guys can solve this for k? I think you can. And I'm going to hook it up with something because there's a shortcut for it, but I think you'll find it.
What is the 6.5 represent?
This is the final amount after 30 years. Because we're using the 30-year mark because we're given the half-life. What do you divide by first? 30? And I'm going to simplify it in the process. No matter what the problem is, I'm pretty sure there's going to come out to be 1/2 on this side. Every single time. If we run through a single half-life, there's half as much left. I'll write it out this time. Like, that's what it would really be, right? And that's 1/2. But check this out. E to the 30k. How do you undo an exponential? By eating lunch and seeing you cool cats tomorrow finish this problem.